Okay, now we come to the other topic about periodic orbits. For this purpose, we will study periodic orbits in more detail for a plane where the trajectory evolves in a plane. So, in other words, at each time instant, x of t is an element of R2. It has two components only. So, what is the objective? The objective is to design robust and stable oscillators. So, what is robust about this and what is stable about this? We want that the amplitude and frequency of the oscillations are not too sensitive to the initial conditions and are not too sensitive to the system parameters. So, as we had noted at the beginning of these lectures, only nonlinear systems can help. Why is that? Because linear systems first of all are sensitive to initial conditions. In other words, if we start with a different initial condition, then the amplitude is different. Of course, for linear systems the frequency remains the same, but the amplitude is different. Moreover, the fact that there are periodic orbits is extremely sensitive to system parameters. In other words, the eigenvalues are on the imaginary axis. For small changes in the system parameters, the eigenvalues could be in the right half plane or in the left half plane, which means that we might have either no periodic orbits and all trajectories go to 0, or the trajectories could become unbounded and there is again absence of periodic orbits. In other words, linear systems are at the brink of instability, and hence periodic orbits are extremely sensitive to the system parameters. So, for nonlinear systems, the question arises how to even claim that there are periodic orbits for this system of equations. So, one extremely important result in this context is the Poincare-Bendixson criteria. So, what does the criteria tell? So, consider the system x dot is equal to f of x, in which note that x has only two components. X here has only two components, and suppose the set M, suppose there is a set M which is a compact set, it is a closed and bounded subset of the plane. Suppose M has the property that M contains no equilibrium points, or M could contain an equilibrium point such that that equilibrium point is either unstable focus or an unstable node. So, there are two situations for the second bullet. The first case is M contains no equilibrium points. The second situation is that when we linearize at that equilibrium point, if there is an equilibrium point, then at most one equilibrium point is allowed, and when we linearize at that equilibrium point, then the linearized system has an unstable focus or an unstable node. In other words, both the eigenvalues of the matrix A, which we get by linearizing at this equilibrium point, are unstable. Both the eigenvalues are in the open right half complex plane. So, suppose M has this property. Further, suppose M is also positively invariant. Yeah, if M satisfies these three conditions, that it is a compact set, it is positively invariant, and either M has no equilibrium points or at most one which is unstable. These three conditions are sufficient to ensure that M contains a periodic orbit. Yeah. So, under these assumptions, the Poincare-Bendixson criteria claims that there is M is guaranteed to contain a periodic orbit. So, what is the intuition behind this? So, M is positively invariant and compact. In other words, trajectories that start inside M remain inside M for all future time, and since M is compact, these trajectories are all bounded. They cannot become unbounded because they do not even leave M, and M is bounded. Further, these bounded trajectories will have to approach periodic orbits, or they can approach equilibrium points. As t tends to infinity, what happens to all these bounded trajectories? They either approach the equilibrium points or they approach periodic orbits. These are the only two possibilities. Why? Because the trajectories are all bounded and they exist for all future time. Now, if we rule out existence of any equilibrium points inside M, then we are forced to have a periodic orbit. This is what Poincare-Bendixson criteria says. Secondly, even if M had a equilibrium point, but if that were unstable, then the trajectories could not be converging to them, or trajectories could not be converging to the equilibrium point. So, we would have a periodic orbit even if M had an equilibrium point which was unstable in that case. So, these three conditions on M ensure that there is a periodic orbit. So please note that this is only a sufficient condition for existence of a periodic orbit. Of course, there can also be a continuum, there can be non-unique periodic orbits, there can also be a continuum of periodic orbits, which we will see very soon. Another important criteria in this situation is the so-called Bendixson criteria. So what does this criteria say? It is a sufficient condition. Please note which conditions are necessary, which conditions are sufficient. The Bendixson criteria is a sufficient condition for non-existence of periodic orbits. Yeah, it is a sufficient condition for non-existence of periodic orbits that are fully contained inside a region. So what is the criteria? If on a simply connected region D of the plane, so we will quickly see what a simply connected region is. So on a simply connected region of the plane, if this particular expression here, yeah, satisfies the condition that it is not identically 0 and it does not change its sign. If these conditions are satisfied, then the system of equations x dot equal to f of x has no periodic orbits lying entirely in D. So inside the region D, we check that this quantity is not always equal to 0 and it also does not change sign inside D. If those two properties are satisfied by this particular function, then there cannot be any periodic orbit lying completely in D. So please note that it is only non-existence fully contained inside D of periodic orbits that is being guaranteed by the criteria. So x dot is equal to x1 dot x2 dot, which is equal to f1 of x, f2 of x. So this is our dynamical system. As I said, we are considering evolution of trajectories in a plane. So x has only two components, x1 and x2, and hence this differential equation has only two equations inside this. So now we differentiate the first one, we differentiate f1 with respect to x1, and to that we add the partial derivative of f2 with respect to x2. So note that f1 depends on x, which is x1 and x2. So f1 can depend on x1 also and x2 also, and similarly f2 can depend on x1 and x2. Hence we have partial derivatives of f1 and f2 here, partial derivative of f1 with respect to x1, partial derivative of f2 with respect to x2. This particular quantity is some function. Yeah? Suppose that function is called g, which depends on both x1 and x2. So what does the Bendixson criteria say? That this particular quantity, you check that g of x1 comma x2 is not identically 0 in D. So D is a region. Inside this region, this quantity is not identically 0. In other words, there is at least one point x1 x2 where this is not equal to 0. As soon as this is not equal to 0, at least at a single point, it means this is not identically 0 in D. It is allowed to be 0 at a few points, at several points. However, it should not be equal to 0 at all the points in D. That is a statement that this is not identically 0. Also check that the sign of G, the sign of G can be equal to either 1 or -1 or 0. Yeah, this is in general possible, but we require that the sign of this should not change. In other words, it should not go from -1 to 1, from -1 to 1 or 1 to -1. As long as it is always 1 or always -1, maybe at some points it becomes equal to 0. If the sign of this does not change when you check for different x1 x2 points in this region D, if these two conditions are satisfied, then the Bendixson criteria says then D cannot fully contain a periodic orbit. There is no periodic orbit that lies entirely in D. So another assumption that we had made was that D is a simply connected region. So what is a simply connected region? So in the plane x1 x2, suppose this is a region D, we will call this region D simply connected. Connected of course means that D should not be made up of two such parts. This is in D and this is in D. So this is not connected, right? Because to say that it's connected, we take any 2 points and there should be a curve, there should be a path between these 2 points, and the points on the path also should lie in D, and this should be possible for every 2 points in D. So if D had 2 components, while certain points are connected by a path lying in D, every 2 points are not connected. Look at a point there, a point here, a path from there to here is forced to go outside the set D. So such a set would not be called connected even. So for a region that is connected, what do we mean by simply connected? So now we take this region D. So we take a closed curve inside this. This is just a closed curve, and this closed curve can be shrunk to a point. We can take a smaller curve, slightly smaller curve. So and this shrinking can eventually lead to a point, and in the process of shrinking to a point inside, at no situation does the curve have to leave the set D. In other words, every closed curve can be shrunk to a point while being inside D. If that is a situation, if that is a property that D has, then we will say D is simply connected. So all these regions that we usually think of are indeed simply connected. So an example of a set D that is connected but not simply connected is a set which has holes. So take this and we rule out this particular case. So what is our D? Our D is this shaded region, and this shaded region without this particular place, without this hole. So this D with a hole, this is our D. This is an example of a region that is connected. Why it is connected? Because we can take any 2 points in D, and there is a path that connects these two, and all points in the path are also in D. But what about a closed curve? Notice that this closed curve cannot be shrunk, cannot be made smaller and smaller such that all the whole curve is in D. Why? Because it cannot be shrunk to a point. So in the process of shrinking this curve to this point, to any point, it turns out that this hole, because it is inside the curve but it is not inside D, inside the region D, we are not able to shrink this closed curve to a point. We might be able to shrink other closed curves to a point, but for the region D to be simply connected, every closed curve we should be able to shrink to a point. So there are curves here which we cannot shrink to a point, hence this D is not simply connected, but this D is simply connected. So the Bendixson criteria requires that the region D for which we are checking is a simply connected region. So on the simply connected region, we check whether the two functions, whether this function G, whether the function G here, which is obtained from f1 and f2 by doing this partial derivative operation, this G should not be identically 0 on this region, and it should also not change signs from 1 to -1. It is allowed to be 0 at a few points, in which case the sign is equal to 0, that is not of concern, but it should not become from 1 to -1 or -1 to 1. If D satisfies these two properties, at all points in D, G satisfies these properties, then the Bendixson criteria says that there is no periodic orbit lying entirely in D. What the Bendixson criteria does not say is that, suppose this is the region G, it is simply connected, region D, and suppose G of the previous slide changes sign. Changes sign means what? When we take different points x1 and x2, then it is equal to 1 at certain x1, x2 points, and it is equal to -1 at some x1, x2. It is equal to -1 at certain other points, at some other points. If G is changing its sign from 1 and -1, then the Bendixson criteria only says us, what it says is that there is no such periodic orbit, there cannot be such a periodic orbit, yeah. But there could be a periodic orbit that is not lying entirely in D, yeah. Such a periodic orbit could be there which partly is inside D and partly outside D. Such a periodic orbit could still exist. The Bendixson criteria does not rule out such periodic orbits existence. It only rules out any periodic orbit that lies entirely in D. This is ruled out, yeah. So please note that there is a subtle difference in lying entirely in D and passing through D, and the criteria only says that if G does not change its sign while being checked in D, then there is no periodic orbit that is contained in D. So let us take an example of a linear system. So the corresponding matrix A, this can be also written as x dot is equal to Ax, where A is equal to 0 1 minus 1 0. So let us check the eigenvalues for this matrix A. So determinant of Si minus A is equal to S square plus 1. So please check that the determinant of this, the characteristic polynomial, turns out to be this. So the eigenvalues of A are plus and minus j. One eigenvalue of A is equal to plus j, the other one is minus j. In other words, there are two eigenvalues both on the imaginary axis, which suggests that there are periodic orbits. The equilibrium point 0, 0 is a center for this particular A. So let us see what happens to the Bendixson criteria. So what is our G, which we have defined as del F1 by del X1 plus del F2 by del X2. So for this particular case, this is our F1 and this is F2. So derivative of F1 with respect to X1 is equal to 0. Derivative of F2, X2 does not even appear in F2, only X1 appears. So derivative of F2 with respect to X2 is also again 0. This is 0, yeah. So no matter which region you take, no matter which simply connected region you take, G of X1 X2 is identically equal to 0. It is equal to 0 without even having to specify at which point X1 X2 we are checking this. So this is a situation where Bendixson criteria is not applicable, yeah. So Bendixson criteria assumptions not satisfied. The assumptions were not satisfied. Does that mean that there are no periodic orbits lying entirely inside that simply connected region D? No, it does not mean that. It only means that because the assumptions of the Bendixson criteria are not satisfied, we cannot go ahead and conclude anything, because Bendixson criteria is not valid, the statement is not valid. However, we know in this particular case that it is identically 0 and there are periodic orbits indeed, yeah. In fact, these are all the periodic orbits. So from any initial condition on this plane, there is a periodic orbit passing through that. In other words, for every simply connected region that contains the origin, as long as this region is some region like this, there are plenty of periodic orbits. However, Bendixson criteria does not tell us that. Why? Because Bendixson criteria assumes that this G is not identically 0, and that situation is not satisfied here for the case of a linear system with periodic orbits, and hence we are not able to use Bendixson criteria here. We will see some more examples of where Bendixson criteria is applicable in the next lectures. Thank you.